Hello Year 11 and welcome to our second video here for our sixth topic. We are still doing coordinate geometry. In our last video we were looking at the distance formula to calculate length and finding the midpoint of an interval. Today we're going to look at gradients of intervals and lines, and frankly this is super important. So much of the advanced and the extension course has to do with ideas around gradients, rates of change, the way that functions change. So much of our work is about these sorts of things, and this is really an introduction to it today. Settle in, it will be a fairly long video, I suspect. Anyway, let's jump into this. So, the gradient of a line is a measure of its slope. Okay, we know that positive rises from left to right. We have a formula here for the gradient, y2 minus y1 over x2 minus x1, the rise over the run, if you like. Now, I mentioned in the last video, with the distance formula, it doesn't matter too much if you mix up the order of the x1 and the x2. With gradient, it very much does. Right, remember, distance, we're really only interested in the magnitude, how long something is. We can't really have a negative one, but gradient, different story altogether. Definitely have negative gradients, and it would be very wrong to describe a gradient without the direction. So here's an example. We're asked to find the gradient of the line passing through these 2 points. So let's call this x1, y1 and x2, y2. The gradient, right, is y2 minus y1, 7 minus negative 5 on 4 minus 1. Again, be extra careful. There'll be negatives here a lot and subtracting negatives and so on. Fractions with negatives, all these pretty simple things that we get wrong pretty easily. So we evaluate that. My gradient is 4. All good. Rightio, here's another part to this question. Now, x1, y1, x1, y1, x2, y2 are going to be 0, 0. So y2 minus y1 over x2 minus x1 gives us negative 4 over 7. Rightio, it's calculating the gradient between 2 points. Next up, we're given the equation of a line in general form, which we haven't used a lot until now. Here it is in general form. It says identify 2 points on the line. Look, this can cause some grief for some students, because like, which 2 points? Well, there are an infinite number of points that lie on this line. Choose any value of x, substitute any x values, I suppose we should say, that belong to the domain, but nonetheless the domain and range of this function are all real numbers. So choose some value of x and calculate the corresponding value of y. I'm going to choose the 2 easiest ones I could think of. Let x equal 0. So we have 3 lots of 0. 3 lots of 0 plus 4y minus 5 equals 0 means 4y equals 5 means y equals 5 over 4. In fact, I'm going to say that's x1 and y1. Now the next x value I'm going to choose to substitute in, you could choose whatever you like, but I'm going to choose x2 equals 1, because that's pretty easy to calculate. So we substitute 1 in there. As I say, remember, you could put 2, you could put negative 3, you could put anything from the domain in there at all. I'm choosing easy numbers, 0 and 1. So 3 lots of 1 plus 4 lots of y minus 5 equals 0. That's a bit messy. That means that 4y equals 2. That means that y2 is 1/2. Okay, now you can see I've got an x1, y1 and an x2, y2. I've found 2 of the infinite points on that line. Now I use the gradient formula, so y2 minus y1, 1/2 minus 5 over 4 over x2 minus x1. You can see choosing the 1 and the 0 here works out nicely because the denominator of my fraction becomes 1. It's nice. I've got 2 fractions in the denominator, 2 fractions in the numerator, the top of the fraction, and they have different denominators themselves, but we can think of 1/2 as 2 quarters. 2 over 4 minus 5 over 4 is negative 3 over 4. Righto. So That one was a little tricky, but again, using the gradient formula and some of these ideas about substituting into a function, I suppose, about the relationship between x and y. Now let's talk about parallel lines. Parallel lines, or two lines are parallel if and only if. That's what IFF means. It's not really a proper English word, but it's a nice maths word. If and only if they have the same gradient. So two lines have the same gradient, they're parallel. Two lines parallel, they have the same gradient. Right? No exceptions to that rule. So I can prove then that two lines are parallel by calculating the gradient of each of those lines and comparing them. Here we go, A, B, C, and D. We want to show that AB is parallel to CD. So the gradient between the gradient of AB, right, y2 minus y1 over x2 minus x1 is a gradient of negative half. The gradient of CD, negative 5 minus 0 over 8 minus negative 2, is also a negative half. So that means that the gradient of AB is equal to the gradient of CD, which means that AB is parallel to CD. You can see how we've set that out there. Show that, right? You don't make any assumptions. You do the calculations, and you usually end by making an equivalence statement here, that this is equal to that. Therefore, right, I can assume that AB is parallel to CD, or conclude. Now, perpendicular lines, somewhat different to parallel. Perpendicular lines meet at right angles. And again, I've got a nice algebraic description of this, that the product of their gradients is negative 1. So m1 multiplied by m2, if that product is negative 1, then the two lines are perpendicular. If the two lines are perpendicular, then the product of their gradients will be negative 1. I haven't got an example there. We follow the same sort of rules. That is something that we will come back to quite a few times over the next few months. Now, collinear points. Collinear means, right, I can't really have two collinear points because collinear means fall on the same line. 2 points will always be on some sort of line. But 3 points, they could either make a triangle or they are collinear. And one way to test for this collinearity is to show that that if I've got 3 points A, B, and C, then if the gradient of AB is equal to the gradient of BC, those lines are parallel, but they also both pass through B, which makes them collinear. So should you ever get a question saying, show that these points are collinear, this is how you can do that. Right, we'll find the gradient of AB, right, 4 minus negative 2 over 0 minus negative 3 is equal to 2. Find the gradient of BC, that's 8 minus 4 on 2 minus 0, also equals 2. And then because the gradient of AB is equal to the gradient of BC, then the A, B, and C are collinear. Righto, now I'm not sure. Yeah, we've still got a little bit to go here. Angle of inclination. So you can see from these diagrams here, the angle formed from the positive end of the x-axis moving in a anti-clockwise direction until we reach a line passing through the origin. This is our angle of inclination. You can see here, alpha here, right? That could also be a reflex angle all the way around here. So the angle of inclination, right? The angle of inclination, which we call alpha, if I took the tan of that angle, I would have the gradient of the line. Conversely, if I take the inverse tan of the gradient, I can find the angle of inclination. And that's probably what we're going to be asked to do, because we're already pretty good now at calculating gradient. So between the origin and this point, we'll find the gradient first, and then we'll find the angle of inclination using inverse tan. So the gradient, we're going to say that x1 is 0, y1 is 0, x2, y2. So y2 minus y1 over x2 minus x1 equals negative 3 over 2. Now, if I pull out my calculator, and I'm still trying to get my hands on an emulator here, if I pull out the calculator and do second function tan, bracket, -3/2, close bracket, equals, I should get 124 degrees. Now, if I don't, if I get something like -56, that's fine. Just add 180 to it, and we'll get the other end of that. We're not probably interested in a negative angle of inclination. We're going to stick with the positive one that might be obtuse or even reflex. Rightio. Now, I need to come back to that. Let's revisit something. I said something before, and I'm just thinking on it, that was not very sensible. Is it going to come back? Yeah, it might. I said it's the angle, so my angle of inclination, sorry, before this video wraps up, we've hit the 10-minute mark, but the angle of inclination is between this x-axis and the line, moving in any clockwise direction. And I said it could be acute here, it could be obtuse over here, or it could go all the way around and be reflexed. But no, it can't be greater than 180. That's a ridiculous notion. Well, it is when you think about it, because imagine that this line swings around, right? I'm not measuring from here around to this point here, because there is an acute angle in here first. I would be crossing over the line. Okay, my angle of inclination on reflection, as I've made this video, the angle of inclination, it has struck me, will always be somewhere between 0 and 180 degrees. But a quick recap of what we looked at in this video. On top of that, we calculated the gradient. That's good, and it's important. We showed that lines are parallel when their gradients are equal. We showed that lines are perpendicular when the product of their gradients is -1. We found that, we showed that 3 points are collinear when the two intervals formed between those 3 points have the same gradient. Okay, we did that. And we calculated the angle of inclination as the inverse tan of the gradient. Okay. That's it, I think. I hope it's made sense. If it doesn't, and there's every chance that I've got something horribly, horribly wrong, please jot it down and ask me during our next conference online. Okay, that's it. Hope you enjoyed. See you next time.